Okay, let's take an example of two-dimensional collision, and let's take a mass m1 with velocity v1 initial, and we have a target here. This is a projectile, the target at rest, m2. I'm going to draw the target a little bit off because I don't want it to be a head-on and one-dimensional, so I'm going to put my target somewhere here. Okay, you see here, m2, v2 initial 0 at rest. Okay, and then there will be collision. m1 will go this way, v1 final, and m2 will go this way, v2 final. Okay, so this is a two-dimensional problem. Okay, two-dimensional problem. And let's take the case where m1 equal m2 to make things easy. So m1 equal m2. Let's say 1 kilogram, for example. We will see, we don't need the mass now. And we take v1. So I have two angles here, very important, theta and phi. Okay, two angles, theta and phi. And we take we take some values here. v1 initial, the speed, v1 initial is 4 meters per second, and the angle theta is 60 degrees, and v1 final is 2, the speed is 2 meters per second, and we are asking for calculate the angle phi and v2 final. Okay, so we have two unknown. Okay, so how many equations we need? We need two equations. Let's write the conservation of linear momentum. So we take this x-axis, right? Positive x, and this is the positive y. These vectors v2 final need components. So it has v2 final, this is cosine phi, and this is v2 final sine phi. Now, by now you should be able to decompose vectors. Very important. Here, this angle theta is here, v1 final cosine theta, and this is v1 final sine theta. Okay, let's write now the conservation of angle of linear momentum along the x-axis. Okay, we need the x-axis and the y-axis. So what is the linear momentum before collision? It is m1 v1 initial plus 0 because the target is at rest equal m1 v1 along the x-axis, v1 final, and v1 final cosine theta, right? And then you have also plus m2 v2 final cosine phi. I hope you understand what is happening here. This is the linear momentum before collision. This is after the collision. After the collision, both the target and the projectile are moving, and they have velocities and they have mass. This is a mass and the velocity along the x-axis. Mass, velocity along the x-axis. And both of them are positive. You can see that the directions. In this direction, positive x. Let's go to the y-axis, and write similar equation. Along the y-axis before the collision, you can see there's nothing along the y-axis. So 0 plus 0. m1 doesn't have any velocity on the y-axis. m2 is at rest. Okay, let's go to the after the collision. m1 is going in this direction, so m1 v1 final cosine sine theta, right? Sine theta. Okay, minus, you see here is down, minus m2 v2 final sine phi. Okay, now since m1 and m2 are equal, I'm going just to cancel them from here, okay? V1 initial is 4. I'm going to put 4 here. Equal, V1 final is 2 cosine 60, right? Theta is 60. Cosine 60 degrees plus V2 final cosine phi. Here, I don't know both of them. I will write them like this. Here, it will be 0 equal what? M1, of course, M1 is gone and M2 are gone because they are equal masses. This is a special case to make things simpler, okay? So, V1 final is 2, okay? 2 sine 30 degrees minus V2 final sine phi. Equation number 1, 2, and this equation number 1. Sine phi here, Sine 60 here, and this is sine phi. Sine 60 degrees and sine phi here. Okay, I'm going to write this one here. V2 final sine phi is equal, sine 60 is, this is 1.73. 1.73. Equation number 1. And the second equation there, okay, this is 1. Cosine 60 is 1. So this is, cosine 60 is half. So this is 1, and this is 4. There will be 3. So V2 final cosine phi will be equal to 3. This is equation number 2. From here, all this is 1. Take it to this side is minus 1. 4 minus 1 is 3. Okay? So I'm going to do 1 divided by 2. I'm going to divide the two equations. Okay? So what do I get? I get from the left side 10 phi equal 1.73 over 3. This will give me the angle phi equal 30 degrees. Okay? 30 degrees. I'm going to put here 30 degrees to find V2 final. Okay? So from there, V2 final will be 3 divided by cosine 30 degrees. Okay? And this will give me 3.46. 3.46 meter per second. That's V2 final. That's the angle phi. This is 60 degrees and this is 30 degrees. What do you notice here? You notice a very important result. When you have a glancing collision and the two masses are equal, this angle here should be 90 degrees. You see here? 60 plus 30 will give you 90. I'm going to do something else now. I'm going to calculate the kinetic energy before and after the collision. Okay? And see what happened now. So let's call K before. Okay? K before is the kinetic energy of this guy here, half mv squared. So it will be 16 divided by 2 plus 0. This is 8. This is 8 joules. K after, we go here. This is half mv squared. V1 final is 2. It will be 4. 4 half will be give me 2. It will be 2 plus half mv squared final. And this will be 6. Okay? 6 joules. This will give me 8 joules. Again, a very important result. The kinetic energy before and after are the same. So here in this problem is actually an elastic collision. This is elastic collision. Okay? Elastic collision. Both kinetic energy is conserved and the momentum is conserved. We have used the result because there are no external forces. This is frictionless. The floor here where the collision happens is frictionless. Okay? So this is an important example. Another example that I want to do now is about, again, collision is in 2 dimensions. Okay? Bismillahirrahmanirrahim. We have another example of a 2-dimensional collision. These are, imagine you have a car and truck coming at an intersection. And we don't hope this happens, but this is an example only. We hope that it doesn't happen. So we have a car here with a mass M1, 1,000 kilogram. Okay. We have a truck here with a mass M2, 1500 kilogram. Okay, both of them are moving with velocities. Okay, here we have V1 initial, this is V2 initial, and unfortunately they meet here at this point. They meet at this point, and they are going as one body here. Okay, together, m1 plus m2, and they are going in this direction here with the velocity v final and the angle theta here. So the question is find v final and the angle phi here, and this is v1 initial is 15 meter per second, and v2 initial is 20 meter per second. So the truck was moving faster than the car, and maybe that's why there was the accident. So this is a two-dimensional problem, as you can see. This is my x-axis, positive x, and this is my positive y-axis, right? Anything to the right is positive, up is positive, to the left is negative, down is negative, okay? So let's write the conservation of linear momentum, because, by the way, this type of collision has a name. It's called a completely inelastic collision, where the two objects stick together. I am sure the kinetic energy here is not conserved in this problem, okay? Not like the previous example where the kinetic energy was conserved. All right, let's write the conservation of kinetic energy along the x-axis, like we did previously. So I have P initial x equal P final x. So what is P initial? We take the first part. The first is m1 v1 initial, right? What is the x component of the momentum of the particle number 2 is 0. Okay, equal m1 plus m2 v final. The component of v final along the x-axis. This is the angle phi, right? This is v final cosine phi. Cosine phi. Okay, cosine phi, and then take it positive, right? To the right. And this will be v final sine phi, because this is opposite to the angle. This is adjacent to the angle. Okay? There's one equation here. In this equation, we have two unknown. We have v final and the angle phi, we don't know them. So I have to write another equation. I go to the y-axis. If I go to the y-axis, and I write P initial y equal P final y. Okay? So what is P initial y? What is the y component of the momentum of this guy here? 0. Right? Plus this guy here is m2 v2 initial equal, okay? Equal what? Equal m1 plus m2 v final sine phi. This is equation number 2. Okay? We can put the numbers if you want. Okay? We can put the numbers here. So I can get v final cosine phi from here is equal m1 over m1 plus m2 v1 initial, and this is exactly this is 1000, this is 2500, 1000 divided by 2500 times v1 initial times 15. Okay, and I go to the other equation here. V final sine phi is equal to m2 over m1 plus m2 v2 initial, and this is m2 is 1500 divided by 2500 times 20, right? 20. So if I divide the two equations, if I call this one, if I divide the two, this or divide by this, so I will have 10 phi, right? 10 phi. The division here will give me 10 phi will be equal to 2. You get 2. This will give me phi, the angle phi, tan inverse of 2, which is equal to 63.4 degrees. That's the angle phi we're looking for. So the two objects will move in this direction, making an angle of 63.4 degrees with the positive x-axis. That's the angle phi. We take this angle phi here and put it here to find V final, okay? Because we know the right-hand side of that equation. If you put that, you get V final equal 13.4 meter per second. So this is the answer. The angle theta is 63.4 and the final velocity after the collision is 13.4 meter per second, making an angle of 63.4 degrees with the positive x-axis. Now, if we want to calculate the kinetic energy before and after the collision, we say K initial is equal to what? Half M1 V1 initial squared plus half M2 V2 initial squared. If you do this calculation here at home, you get 412,500 joules. It's a large number because we have large masses and high velocities, okay? If you look at the kinetic energy after the collision, this is K final, after the collision, it will be half M1 plus M2 V final squared. If you do this calculation, you get 224,450 joules. Okay? You notice one thing important here, that K final is less than K initial. So there's energy lost due to the collision because this is a completely inelastic collision and kinetic energy is not conserved. K here is not conserved, okay? And this is the proof of it in front of you here. The energy which is lost to heat and sound and so on. Thank you very much.